Yeah. Well, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class, for your creation. Just help us to glorify you today, Lord, in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so we continue on with my examples. So, example 1 for today. I have a table, and then there's a pulley off the table. That was supposed to be a level table. Use your imagination. And there's a mass sitting over here. All right. And then I call that mass 1. And then I also have a it's connected by a pulley with moment of inertia I. All right. And then it's connected by a essentially massless rope like that. And then there's another mass, M2, over here. All right. And then the question is, what's the acceleration? All right, so that's the problem. Now, what's new about this compared to what we've done before is now the pulley is not massless, right? So there's a moment of inertia to the pulley wheel itself, and it has some resistance to, like spinning. So the question is, how do you solve a problem like this? We haven't done one quite like this before. So what we need to do is we need to think about, and the question, of course, then there's other questions. Let's see here, to keep things relatively simple, I'm not including any friction. So I'm supposing that this slides without friction. Of course, you could add friction. That would be a different but slightly more complicated problem. Not that much more complicated, honestly. So M1 slides without friction. We're assuming this is near the surface of the Earth as usual. All right, so, and we need to, we're going to need to know like what's the radius of the pulley wheel. That's going to be important. We're assuming that the mass of the rope is essentially negligible. All right. So how do you solve such a problem? Well, what we're going to do is we're going to write Newton's law, Newton's second law for each mass, and also the pulley. So for M1, we have M1A is equal to what? So like what's the free body diagram on M1 look like? You've got this tension right here, let's call it T1, right? You've also got M1G, and you've got the normal force on 1. Of course, the normal force and the weight of M1, they just cancel out. Those aren't interesting to the motion, right? They're just canceling out. So really, we're just interested in tension 1. All right? Now, tension 1 is the tension in this rope, which means that there's also a tension 1 pulling right here like so. All right? So in short, M1A is just equal to T1. That's it. All right? Does that make sense? If I'm defining this as the positive direction, is that the appropriate sign choice there? Yeah.
Why is there the T1
Well, think about it. If you have a rope connected to mass 1 and to the pulley, what does that rope do? It pulls on mass 1, but it also pulls on the pulley. Right? I mean, the rope wouldn't push on the pulley, right? If you think about it. So, now, I know it's a weird thing, but the tension, the mysterious thing about a force is like it puts the tension this way and that way. It's not, the tension is a, the feature of the rope, but it's not like a uniform force that's transmitted along the rope or something like that. That's not how it works. We have to use common sense to decide the direction of tension. Excuse me. All right. I'll do M2 next. M2, A, is equal to what? Well, if you think about M2 over here, right, we've got gravity, weight of M2 going down like that, right? But what else do we have? We have the tension force over there. And, well, the thing to notice is that it doesn't have to be the same tension as the other one, which is why I just wrote T1, because they're both equal to the same thing. No. Sorry, that was supposed to be a 2. Watch out for that. My apologies. So, is there anything else acting on M1? No, I mean M2. No, that's it. There's the tension T2, and there's M2G. And so, given my sign choices, that makes M2G positive and T2 negative, because T2 goes opposite the direction of positive A, right? Which turns over with this pulley like that, right? All right. And then finally, we have the rotational Newton's law for the pulley itself, right? Which says that I times alpha is equal to the net torque on pulley. What are the torques on the pulley? Mm-hmm.
Because T1 pulls on the pulley that way, would T2 pull on the pulley the other way?
Mm-hmm. Very good. Yep. So T2 would be like here for that. Good point. So if I drew it bigger, the pulley, we have T1 up here, and we've got T2 like that there, right? And so here's the center right-hand rule, as requested. I'm not sure this is the one you wanted, though. So if I point my thumb in the direction of the axis, right, and my fingers align with the force, that gives me a positive. That means T1's a positive torque in this direction, right? But what is the positive direction of A? A is like that, right? So that makes the positive direction for the purposes of this clockwise, actually, right? So T2 actually gives me a positive torque, whereas T1 gives me a negative torque. So I alpha is equal to, and they're both of these are applied radially, right? They're both applied distance r from the center point. So I've got RT2 minus RT1. All right? Now, all right, great. How is acceleration related to the angular acceleration of the pulley? Well, A is equal to R alpha is how they're related. That assumes that the rope does not slip. All right? So if I, what's the word? Multiply by R. Wait a minute, no. I'm a dummy. So alpha is what? A over R, right? So this gives me I times A over R is equal to RT2 minus RT1. That feels funny. Let me think about it for a second. No, it's fine, it's fine. So like a typical moment of inertia is like mr squared, right? So I think that still makes sense. Okay, so then, great. If I divide this thing by r, what do I got? I've got I over r squared, right, times A is equal to T2 minus T1. All right, so let's recap. We've got this equation, and that equation. We've got 3 equations and 3 unknowns, but they're not bad, right? Let's label these equations 1, 2, and 3. What do you think we should do? I think we should just add them all. Let's add all 3 equations. What happens? I have got a commonality of A, so I've got M1 plus m2 plus the moment of inertia divided by r squared, all times a, is equal to, what happens over there? The t1 and the minus t1 cancel, the t2 and the minus t2 cancel, and we're just left with m2g. Therefore, the acceleration of this system is simply m2g divided by the sum of the masses and the moment of inertia divided by r squared. There you go, that's the acceleration in this context. This is example 1 for us today, but it's also example 6 of my lecture 28. Any questions about this? What would happen if the moment of inertia is 0? Then we'd be right back to where we were before. Right? If the moment of inertia is 0, that makes T1 equal to T2, so we just talk about a single tension as we did before in these kind of problems. All right? And you could see that the formula, if we had worked this problem before, you'd see that you got the answer we had before without inertia. Another example, let's see here, example 2, very similar example. If you have the Atwood machine, but this time with a massive pulley, all right? And we'd say I is equal to 1/2 mr squared. So this time we'll take the pulley to be, I was intentionally vague about example 1. I didn't tell you the geometry of the pulley, right? But if the pulley is a disk, if it's a solid disk, then the moment of inertia is 1/2 the mass of the disk times r squared, right? So is that. And so here, almost the same as the previous example. I'll go through this one quicker. We'd have m1g down like this. We'd have t1 up like that. Over here we'd have m2g like that. We'd have t2 up like that. And on the pulley, we'd have a t1 on this side, and we'd have a t2 on that side. So, however you guys want to define, I tell you what, just for the sake of experience, let me define A to be positive in the other direction for the sake of, thinking about. This time I'm going to make A be positive this way, okay? Okay? So with that choice of sign, excuse me, goodness gracious, M2G is equal to, oh my bad, M2A is equal to M2G minus T2. And then on M1, we have M1A is equal to T1 minus M1G. And then, of course, we have the angular equation, which I'm going to write over here for a minute, and then we'll put I'm going to write the angular equation over here. I'm going to clean it up, and then I'm going to put it over there to add the equations again. So we have I alpha is equal to the net torque. But in this context, that's 1/2 mr squared alpha is equal to, well, let's see here. So this time, again, the radial arm is r, yeah? And this time T2 gives me a positive torque. So I have RT2 minus RT1 from the other one. Then if I remember that A is equal to R alpha, right? If I have A is equal to R alpha, what do you got here? You have 1/2 MRA. 1/2 MRA. So take that equation, divide it by R, and you get big M over 2A is equal to T2 minus T1 for this massive Atwood machine. And then I add these like so. Don't tell the other math professors. M2 plus M1A. You can tell the physics guys, they don't care. M over 2A. So we just factor the A out. And on the other side, the T's, they be canceling. And you're just left with m2 minus m1 times g. Lo and behold, the acceleration is m2 minus m1 times g divided by m2 plus m1 plus the mass of the pulley divided by 2. Now maybe you guys have done the Atwood lab. Yes, no? So you're up against this, you know, the moment of inertia of the mass of the pulley itself matters actually. It's part of the thing that keeps you from having exact balancing, right? Because this does play a role. It's there for what it's worth. And if the mass of the pulley is comparable to the masses involved, it becomes a significant thing, yeah? But on the other hand, if the mass of the pulley is 0, we're right back to plain old standard massless pulley Atwood, right? Which is just the difference of the masses divided by the sum of the masses is the acceleration. So for instance, and this is still true, if the masses are equal, the acceleration is, like if m1 and m2 are equal, obviously the acceleration is 0. Yeah. All right, so I have this example in the typed notes, but I don't have a picture for it. So I wanted to do it for you guys today. Another example, and this is example 7 from my handwritten notes, is this. So I guess it's example 3 for us today, which is this. Suppose engine makes torque uh, 678 Newton meters. All right, that's your torque. And this is achieved at an angular velocity of 4,500 revolutions per minute, right, RPMs. Find the power output. Find power output. How many light bulbs, how many 100-watt light bulbs would produce an equivalent energy output? All right. So I don't think we've quite talked about this yet. Let me walk through it for you. So how much work do you get if you have a force and you apply that force over a little arc length? Then that's the work done. Work is FDS, right? Force times distance is the work done. Now, assuming that that force is, so if we're talking about circular motion, right, then we can trade the S for an R d theta, so we have F R d theta, all right? And that's the torque times d theta, which tells me then, if I divide this by t, I get that dw dt is equal to the torque times d theta dt, assuming the torque is constant. In other words, the work done per unit time is the torque times omega. Here's a formula for you. The power output, the energy per unit time, by a torque tau producing angular velocity omega is simply tau times omega. This is the analog. Do you remember the formula we had before? Like power was equal to force dot velocity. This is essentially this is the analog of that equation, right? Like if the velocity is, well anyway, let me just say it's the analog of that equation. I don't want to pursue that further, but okay, so great. Then we can figure that out. Our torque is 678 Newton meters, and the angular velocity is 4,000 revolutions per minute. But of course, we don't like revolutions per minute. We want to trade that for 2 pi radians per revolution and convert that there minute to a minute divided by 60 seconds, multiplying by 1. And if you multiply those lovely numbers out, you get 319.4 kilowatts. So how many 100-watt light bulbs? So you need approximately 3,195 100-watt light bulbs. Of course, this is becoming increasingly meaningless because for reasons that only a retailer could explain, we've decided to label the wattage of light bulbs not in terms of the wattage that they actually require, but in terms of the perceived wattage that would have been delivered by a hypothetical incandescent which no longer exists in stores. So when you buy a 100-watt light bulb, it doesn't actually pull 100 watts, does it? It pulls like 15 watts. So if you want to adjust this for LED bulbs, I think we need like 18,000-ish, 15,000-ish light bulbs. I don't know, but let's not do that. We really should label light bulbs by lumens, by the actual intensity of light they produce, right? That would be far more meaningful. But then people wouldn't be able to cheat and exaggerate their product, would they? So we can't have that.
They would find a way.
They'd find a way? All right. Excuse me. Let me use the projector here for a bit. I wrote up some notes. I should use them. Confession, I'm not going to office hours because I plan to go look at the sun. So, but I will be back to office hours about 3:30. So, you say I should end class early? But that has nothing to do with the eclipse. You guys can't fool me. You have an exciting date tonight. You need to get home and freshen up and stuff, right? That's what it is. Here. Come on, work. And does that QR code work?
Oh no, not this again.
I got you.
It's a YouTube link that I don't trust it.
Whatever could there be in a YouTube link?
Wow. I got a rickrolled in the bathroom at a gas station 2 days ago, so I'm not doing this again.
I do want to get like 100 I want to I want to print out I need to take some measurements of the signs that Cassis puts up for tutoring, so that I can find what the size of the QR codes are on their announcement, and then I want to print out 100 of these stickers with a certain QR code, so I can just find signs like that and just put my sticker over it, and just walk away.
Do it during the next CFA.
Do it during CFA? I like the way you think. How many people would you need to sync if you wanted to rickroll Convo? How many students with simultaneous cell phones playing the song would you need to effectively do it?
They do it for coffee house.
Like 1,000?
Instead of uploading your application,
Not believe it. Yeah, just load it.
Hack to do it while you guys up there.
So guys, all right, so I talked about this a little bit. I want to talk about it again because I haven't talked about it enough. So one of you asked me what the right-hand rule was. It depends on which one we're talking about, all right? So if we're talking about the right-hand rule in 3 dimensions, the right-hand rule in 3 dimensions says that if I take vector A crossed into vector B, A crossed into B, I take my right hand, direction of A, I cross it into direction of B. Whatever way my thumb points, that's the A cross B direction. That's one of the right-hand rules. So right-hand rule, A crossed into B, thumb points in the direction of A cross B. That's one right-hand rule. Another right-hand rule is that if you point your thumb in the direction of the pivotal axis, then your hand will curl in the positive sense of the rotation. So I point my thumb, I grip the axis, if you can imagine it coming out of the board at you, then your hand will curl in the positive sense of the rotational direction. So this force produces a positive rotation because it has a part of the force which is perpendicular to the radial arm, and so that produces a positive torque, this kind of twisting way, right? If on the other hand, you could imagine that we had this point here as a pivot, right? So I got my radial arm like this, and if this was the force that was applied, right, then as I grip the axis that's imaginarily going into the board and circle my fingers into the direction that F is pointing, I'm creating a negative torque, right, if I define out of the board as positive. So the cross product, though, like how do you visualize the cross product? The cross product, see, if we move this R here up to here, all right, then this angle right here is what we call phi. So the formula is torque is equal to R cross F, right, which as a formula is RF sine phi in the direction given by the right-hand rule. So if you just care about the magnitude, you just need to calculate the distance, the force applied, and then times the sine of the angle between the force and the radial arm, right? It's the angle between the force and the radial arm that matters. That's what tells you how much of the force is actually perpendicular to the radial arm. Okay? Does that help with, I'm not sure which right-hand rule you're asking me about. You asked me before class. Did I answer it or no? All right, who asked me? All right, well, I know. Okay. I might have been dreaming. It's okay. Let's go on. So next up here, this example 7.62 is precisely the massive Atwood machine that we just worked out over there. Okay, so there it is typed up without a picture. 7.63 I want to talk about to you guys. So here we have, like, if you can imagine like a coffee can full of cheese or something, or take a coffee can, fill it full of cement, you know, and then maybe affix a copper nugget or something to the rim of it. All right, so like you've got a coffee can with a uniform mass density, a cylinder like that, and then I'm affixing a point mass to that on the rim, and then I want to study the motion. I'm assuming it rolls without slipping along a plane. So, excuse me. All right, so as we think about the motion of the cylinder with the point mass attached, if you think about gravity acting on the totality of the cylinder, it's torquing to the left one side and it's torquing to the right the other. So the net gravitational torque on the cylinder is 0 by symmetry, right? So all of the torque on the cylinder mass system are completely coming from gravity acting on the little mass. All right, so I can calculate the torque on the system by that. Now what's the moment of inertia for the system of the coffee can or the wheel of cheese with the mass attached, whatever you want to think of it? Well, it's the little mass, r squared, because it's affixed at the rim, right? So the moment of inertia from the little mass is just little mr squared. And why do I have 1/2 big mr squared? Well, I'm assuming it's a uniform mass, right? So it's like a moment of inertia for a disk, solid disk like that. And this is the rotational Newton's law. I alpha, what is d squared t, d theta squared dt squared? That is the angular acceleration. So I have the moment of inertia times alpha is equal to the torque. Now I say that the torque is mgr cosine theta. Does that make sense? Look at the picture. Look at how I've defined theta, right? So since theta is there, this is a right triangle. Theta is also down here. Mg is the hypotenuse. So the tangential part of the force apparently is mg cosine theta. I multiply by r because the gravity force is pulling on the little mass a distance r from the center of the rotation here. So anyway, after all that, I'm faced with this lovely differential equation. D squared theta dt squared is mg over the sum of m plus m over 2 r times cosine theta. Now, I would love to tell you that when you take differential equations, you're going to learn how to solve that, but that's just not true. This equation's too hard for us. This is a nonlinear differential equation because it's cosine of theta, which, understand in terms of calculus 2, that's an unending power series of theta, right? That's actually very difficult to solve directly. I don't know if I can. However, what I can do is I can find small angle approximations for it, or I can find the approximate solution for a given theta. And this is important to engineering and physics, as we like to do this. We like to think about a special case. So one special case we could think about would be theta equal to like pi over 2. So minus pi over 2, really. Excuse me. So I introduce, so if I want to center the solution at minus pi over 2, I add pi over 2. I know it's kind of counterintuitive, but it's kind of like factoring, right? If 2 is a 0, we factor out like x minus 2, that kind of thing. Oh, if you guys have a Taylor, do you guys do Taylor series yet? In Calc 2? Not quite? At some point soon, you will talk about Taylor series. If you want your Taylor series to be centered at minus pi over 2, you have to look at powers of, oh man, thing plus pi over 2. What the what? Seriously? Oh, I forgot to plug it in. It's my fault this time. Come on. Come back to us. Don't leave. Don't leave.
I'm already at the door. Want me to just like,
Why leave? I mean, you can leave if you want to, but.
close your eyes. That's what I-
All right. I was going to end early. Anyway. So, all right, so we expand at minus pi over 2. And if you do that, that changes your cosine theta to a minus sine beta. So with this substitution, replacing theta with beta plus pi over 2, this becomes, the differential equation becomes d squared beta dt squared equals minus omega squared beta, where I've introduced omega to be the square root of this jazz right here. But that is the kind of differential equation we already solved for the harmonic oscillator, where we talked about this, sines and cosines being the solutions. And as such, this is the solution. And the frequency is simply 2 pi over that omega. And so there you go. That's the frequency. That's the period with which, like a cylindrical wheel of cheese with a mass attached, that the mass is close to the bottom and it's just rocking back and forth a little bit. That's the period with which it would rock if it's rocking without slipping motion. So we can solve periods for pendulums that are more interesting. Oh, and then you got Mr. Top Hat. Anyway, hey, I set an alarm that's supposed to go off. Why my alarm to go off? What the what? Dudes, that's not cool. Oh, wait a minute, I still got 8 minutes, never mind. All right, so he's got me off my game. Let's talk about these examples, then we'll be done. So here's Mr. Top Hat. He's, as you can see, he's tiny, or either he's tiny or the wrench is large. Anyway, relative to him, the bolt is large. So the question is, how much torque can Mr. Top Hat put on that bolt if he's only got 100 newtons to, press down on? And the answer is yes, because it totally depends on how long the lever is, right? The longer the lever, the more the torque, right? Because we have, if we assume that he's torquing it at near zero angular acceleration, that means that for the fulcrum here, we can work it out. We can make the output force 100 times the input force if we put the distance of the force applied from the pivot point and the force applied from the pivot point. If we relate L and R in a certain way, let's work it out. So to work it out, the sum of the torques is 0 because we're assuming we're just barely moving it, all right? So the angular acceleration is really close to 0. Excuse me. So the output force here is going up, and the input force is going down. So one of these is a positive torque, and one of these is a negative torque. Apparently, I have chosen clockwise to be positive in my picture. All right, great. So the point is that these have to have different signs, which then means, of course, that F out times L has to be equal to F in times R. So solve for R, and you get that the distance of the applied force from the pivot point has to be 100 times further away than the pivot point to the point of application. So you get a force multiplication of 100 times if you've got this set up, right? Now, obviously, this puts like incredible pressure on the pivot point, for one thing, in terms of like practical application of this. Also, I think you know from working with anything, if you've got something that's 100 times further away from your point of application, like it's going to be really, really hard to be accurate in your application of the force, right? It's like super shaky and junk. But nevertheless, it's possible. And there's nothing stopping you from making it 1,000 or 1,000,000. And so it seems like, in principle, that you've got a way to create something from nothing. But yeah.
Why does it say we need a lever length of 101 L to accomplish this feat?
Because you've got 100 on one side and L on the other, so 100 plus 1, 101.
Is that L distance? Is it
L,
back into the bolt?
L is the distance from, I'm not talking about the bolt per se here. So for the bolt thing, admittedly I changed examples, fair enough. But the same principle applies to the bolt. Let's see here.
Oh, that's different.
Yeah. For the bolt, I guess I should think about the wrench actually hits the bolt a certain distance from the center of the bolt's twisting, right? So the little L would be something like the physical diameter of the bolt, or radius of the bolt, perhaps, whereas the R would be like the length of the wrench. What happened? Something happened here. Something definitely happened. All right.
He's back.
Wait a minute, what? All right. Okay. Oh, I see. Oh, I didn't see. Okay, very nice. I feel like it's taking me back to a bad time. Like it feels like COVID again. Like this is horrible. It's the worst. Ugh. Okay, so this one here is not for free. So you notice that while we have to apply the force of 100 newtons really far away to get, if we apply 1 newton 100 times away from where we apply it, if we apply it 100, good grief. So the point is that the output force is applied over a much shorter distance than the input force. And so there is nothing for free. Like the power applied is the same. Like the power is basically, it's just what we were talking about over there. Like power is the force. The power applied for it by a torque is Fr d theta. So, oh goodness gracious. I'm sorry guys, I've lost my spot. So my point here was for that previous example where we have the pivot point 100 times as far away from the point of the force being pushed on the lever as compared to the other point where I call the point of application. The distance that you actually apply the input force is 100 times further. Well, anyway, 100 times the output distance is equal to the input distance. See, so yes, you get 100 times the force, but you also have to do it over 100 times as far. So you don't actually create any energy from nothing. Like it's just, yes, there's force multiplying, but there's also distance multiplying on your part. This is just like pulley systems, right? You ever guys seen pulley systems where people are just going through rope to like lift a car or something? Or whatever, you've seen these block and tackle systems? Well, in order to lift a very large mass, they have to apply a relatively small force, but they have to apply it over many more much more distance. Like they might have to apply, 50 or like 50 newtons, or let me not say that. Let's say they might have to apply like 40 pounds over 40 feet just to lift it an inch or something, right? So this is how block and tackle. The idea of this is how block and tackle systems work in terms of force multiplication. It doesn't come for free. It comes over applying the force over a longer distance, which is what the pulley systems allow you to do. Anyway, that's it for today. Let's go look at the sun.
My glasses.
Yeah, probably.